Welcome. This is the first or the beginning of the graph theory unit. And I want to start out with some vocabulary and a little quick expert definition. In the modern world, planning efficient routes is essential for business and industry, with applications as varied as product distribution, laying new fiber optic lines for broadband internet, and suggesting new friends within social network websites like Facebook. This field of mathematics, which is graph theory, started nearly 300 years ago as a look into a mathematical puzzle. We'll look at that in a bit. The field has exploded in importance in the last century, both because of the growing complexity of business and the global economy and because of the computational power that computers have provided us. So we're going to see that this isn't the only thing graph theory is good for. There is scheduling that we're going to be using graph theory for. There is modeling projects. There is many applications that we can use graph theory for. But to start out with, we want to get into just the vocabulary. There is a lot of vocabulary with this new unit. I want to make sure that you understand all of that vocabulary. So starting out, vertex, and you've had this word before. Vertex, that is in a graph. A graph is made up of points, and those points, where they're connected, are called a vertex for one, or the plural, vertices. Some refer to them as nodes. So if you have a problem that asks you about the nodes or a node, that's the same thing as a vertex. So in this graph, we have 1, 2, 3, 4, 5, 6 vertices or 6 nodes. The edge are the connections between vertices. So connection with vertices, right? Repeat that. So there is an edge from A to D. They are connected. There is no edge from C to D, right? There's an edge from F to C, and F don't have an edge. Now these edges in this graph, they're straight, they cross and everything. They could be drawn curved or in other ways right, to make you understand the graph better, how it might be laid out. If the graph represented roads, they might curve like the roads. And then where these edges intersect, that's not really an intersection. Think of this as one must be passing over the other or under the other, because without a point and a letter to represent the vertex, there's no vertex there. So if you're traveling from A to D, you can't change directions here like you're on an interstate. There's no exit to change here. That's just a road passing under the interstate. Now, also, the vertices, they're going to usually be capital letters to represent the vertices. Sometimes they will use lowercase letters to represent all the edges. You might see an A here, B, this one is C, and that would count for that whole edge from, call this one D, from A to D. But it's just random naming. You know, this one could be E, even though it has nothing to do with E. And you might see the vertices as numbers, vertice 1, 2, 3, and you'll see that later. All right, so those are vertices and edges. And edges will always go between two vertices. One edge can't join more than two vertices. So degree, when we start talking about degree, and again, this can also be called valence. There are Two different words that mean the same thing in graph theory, but the degree of a vertice, and the degree describes the vertices, is the number of edges that connect to that vertice. So you would say that A has a degree of 3 because there are 3 edges. B has 1, 2, 3, 4 edges, so its degree is 4. F would be 4, E is 4, 3, C is 2, right? 1, 2, 2, that's the degree. Number of edges. Number of edges connected to the vertice. The word adjacent means that those two vertices have an edge between them. And that doesn't mean they have to be beside each other. E and D are adjacent, or DE. DE is an adjacent edge. It makes D adjacent to E because they're connected. But D is also adjacent to F, right? Because D and F are connected with an edge. D is not adjacent to C because there's no edge connected. So adjacent vertices connected with an edge. So those that we've had are called simple graphs. Simple graphs. Simple graphs are ones that do not have loops or multiple edges. So these two things change it from being what we've been looking at, just a simple graph, to these non-simple graphs where they might have a loop. Like if Q were connected to Q, that's called a loop, where it's just one edge that, right? So we can make Q go to R, R to N, M. However that graph is drawn, and maybe there's a loop at P also. So it just means if you traveled, you would just go right back to where it was. All right. So that's a loop. This is a loop. This vertice has a degree of 4 now because the loop gives it 2, and then it has 2 edges coming out. Now you can also have what are called multi-edges. If we had 2 separate edges going from R to N, that's just a multi-edge. So now N would have a degree of 3 because there are 3 edges. Even though 2 of them go to R, you still count them. R has a degree of 1, 2, 3, 4, 5 in that case. And be careful, they don't have to go right beside each other. If, and I know it'd be kind of crazy, but if I drew an edge from N over to M, that would change. Now N has a degree of 4, and that is a multi-edge because there's this edge goes straight to M, and then the roundabout edge goes all the way around. So that's a multi-edge. So be careful about the loops, how they change the degree. Multi-edges change the degree. But for the most part, we are going to stick to simple graphs. All right, connected. A graph is said to be connected if there is, and we're going to talk about this word later, but if there's a path from every vertice to every vertice. In other words, if you're at A, can I get to B? Sure, that just takes one edge. Can I get to C from A? Well, I can't get directly there, but I can go from A to B to C. So A is connected in some way to C. Is A connected to D? Sure, you can get straight there. Same with F. I can't get there straight with one, but I can do two edges to E, right? So is B the same way? Well, yeah. If A is connected to every single one of them, then every single one of them can get to another vertice, even if they have to go through A, right? So this graph is connected. Everything is complete, on the other hand, and we use a K to represent complete, but a complete graph means that there is one connection. Every vertice is adjacent, right, to every other vertice. So A has to be joined to B, A would have to be joined to C. So this is not a complete graph because A is not joined to C. A goes to D, A goes to E, A needs to go to F. So we're missing some. So if we had to complete this graph, A would go to F, A would have to go to C, B to C, B to D, E, F, and A. That's good. C would have to go to, well, we already know it did A and B, so I just need to go alphabetically. Has to go to D, has to go to E, and it already goes to F. D would have to go to E and F, and E goes to F. That's a complete graph. Now to make a complete graph, how many edges did I use? So let's look at that. Sometimes it's hard to count up all the edges. You could use maybe a highlighter and highlight them as you go, but once you highlight them once, it's hard to undo that. So K2, a complete graph, which is K2, means you have two vertices. And to make it complete, you just have to join them to each other. That's a K2. So there are two vertices. There is one edge. What's the degree of every vertice? Well, just one in that case. And then what is the sum? Let's do the sum of all the degrees. So if that has a 1, that has a 1. The sum of the degrees for all of them would be two vertices, 1 degree each. That's 2. K3, 1, 2, 3 points. All have to be joined. That's a K3. So the vertices, there are 3. How many edges did that one take? Well, it took 3 edges that time. What's the degree of each one of the vertices? Well, each one is 2. Well, that makes sense because every vertice, if there are 3 of them, this one is going to have to join to 2 others. This one is going to have to join to 2. This one joins to 2. And then what is the sum of all the degrees? The sum of all of them, 2, 4, 6, right? Or if there are 3 edges and the degree of each one is 2, 3 times 2, 6. Yeah? So let's look at a K4. So you'd have 1, 2, 3, 4 vertices. You'd need 1, 2, 3 edges from that one. 4, 5, 6. So K4 has 4 vertices and 6 edges. The degree of each one is always 1 less than the vertices. So if a K4 has 4 vertices, each one would have a degree of 3. And so the sum of all the degrees, well, if you have 4 vertices with a degree of 3, 4 times 3 is 12. So this, of course, K4 has 4 vertices. The degrees being 1 less, that's not bad, right? The sum of all the degrees, that's just a multiply. It's this number. How do we know how many edges? Like if you have a K7, how would you know how many edges it would take to make a K7? Well, if you think about, like, if I number these 1, 2, 3, and 4, that first one had to connect to 3 different vertices. Then the next one only has 2 left, and the next one has 1 left, and so forth. So if you have a K5, the first one would have to connect to 4, and then 3, and then 2. So the edges for a K7, well, that first vertex is going to have to connect to all other 6 of them. And then the next one, since it's already connected to the first, would have to connect to 5, and then 4, 3, 2, 1. And you could add them up. 11, 15, 18, 20, 21. So K7 would need 21 edges to complete it. So I know it would have 7 vertices. It would need 21 edges to make it. The degree of each vertice would be 1 less, 6. And the sum of those degrees would be the number of vertices times the degree. So, but that 21. Well, if you have like a K20 and you're wanting to know how many edges would it take to make a K20, well, doing 19 plus 18 plus, that gets to be troubling. And what we find is that this, when you start adding all the way down to 1, it's not a factorial, you're not multiplying, it's actually a combination. This operation is also 7 choose 2. And this operation then, if you wanted to know, would be 20 choose 2. Always choose 2. And like we said before, 20 choose 2 is 20 times 19 divided by 2 times 1. The 2 would reduce the 20 to 10 times 19. So there would be 190 edges to make a K20, which is the same thing as doing 19 plus 18 plus 17 plus 16 plus 15, so forth. All right, so K complete graphs. These are complete graphs. The next vocabulary word, complement. And we talked about complement in set theory. And complement, or sometimes they call it the inverse graph, the inverse of this graph, is just what is the graph that you could make. So you have to use all of the vertices so that together they would make the complete graph. Or think of it as what edges are missing from this graph. So the complement, and I'm going to put them kind of in the same place if I can, D, E, F. So if that's A, B, C, D, E, F, well, A is joined to B in the original graph, so it would not be joined to B in the complement. A doesn't go to C, so the complement has all of the edges that the original graph didn't have, that together they would make a complete graph. A already goes to D, A goes to E, A doesn't go to F. So I need AF in the complement. Of course, I don't have to go backwards because once we check A, we just need to B, check all the ones after it. B already goes to C, B doesn't go to D, B goes to E, B goes to F. C doesn't go to D, so I'm going to connect those. C doesn't go to E, so that needs to be connected. And right now, if I ask, is this graph connected? Yes, because now every one is in some way connected to the other. C goes to F, so I don't need that. D goes to E, D goes to F, so that's good. And E already goes to F. So those are the 1, 2, 3, 5, right? 1, 2, 3, 4, 5 edges that I would need to make a complete graph. So this is 6. So a K6 needs 6 choose 2, 6 times 5 divided by 2 times 1, or 30 divided by 2. So I need 15 edges. Well, counting up edges might be tricky in graph theory if they're all over the place. You might have to think about if it's a simple graph. So this is a simple graph, no loops, no multi-edges. The degree is 3, the degree is 4, degree here is 2, 3, 4, 4. So that's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the total degree, the sum of all the degrees is 20. And this is why I was talking about that. What's the sum of all the degrees? Well, if each edge gives you 2 degrees, like this edge gives you a degree for A and a degree, then if I divide by 2, that must be 10 edges without even counting them up. So if I find the sum of the degrees of all the vertices and divide it by 2 in a simple graph, that's how many edges I have, 10 of them. Well, if I need 15, right, if you need 15 to make a complete graph, how many edges are in the complement? 1, 2, 3, 4, 5. You can count them up, or you can just use that fact. I have 10 edges already. I need 15, so the complement must have 5 to make up the 15. You could also count up the degrees, right? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The sum of all the degrees of this one is 10, divided by 2 is 5. All right, complement, inverse. Those two graphs are complements of each other. So these next couple of slides, you have 6 vertices in this little graph. I want to go over the vocabulary walk, trail, circuit, path, and cycle. Now, the walk and trail we won't use as much as the circuit, and then the path and the cycle we use it. So walk. Um, a walk is, all of these are, if you pick a starting point and go over your graph, a walk just goes all over the place. There are no rules to a walk, right? So let's say you start at 1 just because people like starting at 1. Um, right, so if you walk, or if you go to 2, down to 3, to 6, to 5, back to 3, back to 2, right? So I did 1, 2, 3, 6, 5, 3, 2. That's called a walk. It goes, there's no rhyme or reason. It can repeat, go over the same edge twice. I went through 3 a couple times. None of that matters, right? That's just a walk all over the place. So a trail is important that you can't repeat edges on a trail. No repeated edges. So if I was going to create a trail from number 1, I could go over to 2, down to 3, to 4, to 5, back up to 3, down to 6, and even go back to 5 where I would be stuck because now I can't repeat an edge. That's a trail. So that was 1, 2, 3, 4, 5, 3, 6, 5. And that's fine as long as, and I could do little arrows so you can see the direction I'm going in, to 4, to 5, back up to 3, down to 6, back to 5. That's a trail. Starts at 1, no edges repeat. And it's important when I got back to 5, or when I went from 5 up to 3, if I would have went up to 1, it's still a trail, but it has an even more special name. It's called a circuit because that's going to be when I close in the trail. All right, so like I said, circuit you can think of it as a closed trail. Closed means start, end, same vertex. And then the trail is no edges repeat. So again, start here at 1. So I could do 1, 2, down to 3, over to 4, 5, over to 6, back up to 3, which is fine. I can go through the same vertice twice, and then up to 1, and I finish at 1. So 1, 2, 3, 4, 5, 6, 3, 1. That's a circuit because it starts and ends at the same place and it won't go over the same edge twice. And of course, if that's a circuit, then I could always do it backwards and it would still be a circuit, right? 1, 3, 6, 5, 4, 3, 2, 1. Same circuit, just in the reverse order. So that's walk, trail, circuit. All right, so now a path and a cycle. What makes a path different than a trail is that this time not only are no edges repeated, but in a path, no vertices repeated. So again, if I were to start at 1, as long as that's a path of length 1, right? 1, 2. 1 to 2 to 3, that's a path of length 2. I could come on down here to 4. That's 3, path of length 3. Down to 5, that's a path of length 4 edges to make that path. Come over to 6. 1, 2, 3, 4, 5 edges to make that path. I have to stop there. I can't go back to 3 because that would repeat that edge. So that's a path. 1, 2, 3, 4, 5, 6 in that order. And there's a lot of other ways that I could do a path. So, like I said before, if it's connected, there has to be a path from every vertice to another vertice. And like here, you can make it from 1 to 2. That'd be a straight path. You can go to 1 to 3. You can make it from 1 to 4 in 2 steps, 1 to 5 in 2 steps, and 1 to 6 in 2 steps. So there is a path to all of them. And when you write it out, you'll see that none of the vertices would repeat in the path. So for a cycle, it's just a closed path. And we already talked about what closed means. So it has to start and end the same vertice. And if it's a path, so start, end, same, right? That's closed. And no edges repeat. Oh, repeat. No vertices repeat. So there's no way for this one that I can make a cycle that would go through everything and get back to the beginning. Even if I started at three, once I went up to one, two, and back to three, right? So if I start at three, but that's a cycle right there. That's a cycle. So does this graph have a cycle? Yeah, but it's not through, you don't have to use every vertex. So any of these, path, cycle, none of those, unless it has a special name, which we're going to talk about later, but right now, just any. So is there a cycle with three? Yeah. Clear that off. I could make a cycle down in the bottom part with four of them, right? Once this goes away. So starting at any one of them, doesn't matter with a cycle. So if there's a cycle from three, four, five, six, back to three, so that cycle is three, four, five, six, three, then there's a cycle that starts at four and goes four, five, six, three, four. And there's one that starts at five because any point on the cycle could be the starting point. So So for this graph, what would it take to create a cycle that goes through that you could get all of them involved? You can't have this three being the branch out, right? You'd need like one edge from one to four. If there was an edge from one to four, then we could start right at one to four, five, six, back to three, up to two, back to one. Ignore this one. But yeah, so that would make a cycle possible. All right, so path, cycle, circuit, know those definitions. Next, we have a weighted graph. And we're not going to go too much into this, but just understand that edges don't necessarily um, they might have like a length. This 8 represents this edge, and maybe that's 8 miles, maybe that's 8 feet, or maybe it's a cost that's $8. Or so we can weight the edges, and you can't look at edges and think, oh, this EG is a lot shorter than AB, so it must have a lesser weight. We don't know that. So you can't just look at edges and assume. But you can get total weight. Like if I did a circuit from A, B, E, C, F, what is the total weight of that circuit? You would just add up all those edges. 8 and 12 is 20, 6 and 5 is 11, so that'd have a weight of 31, right? 8, 6, 12, 5, 31, whatever the 31 represents. So we can add them up, and we'll be doing that a lot. But just so you know, graphs can be weighted. The values, each edge needs a representation. That's a weighted graph. Just like set notation, set theory, we can do a set notation for graphs. And we can put the vertices. This is the set of all vertices. So if I was going to draw this, I would have to have 6 different vertices, 4, 5, 6. I usually draw them in a circle pattern, and that way you can make sure that an edge to each one of them is easy to do. What did I skip? D, E, F, G, H, I. Okay, so each one of them you can make it without repeating. If you put two vertices in a or three vertices in a line, it's going to be hard to tell what the edge is joining. So nice circle pattern when you're having to draw your own. And then the other set is the set of edges. So you have an edge from D to E, D to G, D to H, E to F, E to I, F to G, F to H, G to I, and H to I. Well, that's it. So you can take a graph and break it down into set notation, or take the set notation and draw a graph from it. And just like in set theory, the complement are all of the possible, the missing edges that we could have in that set. And of course, if this is 1, 2, 3, 4, 5, 6, a K6 would have, I think we already did this one, 15, right? 6 times 5 is 30 divided by 2. There are 15 edges. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would need 6 edges to make the complement. All right, so that's sets with graphs. And the last part is, of course, matrices. We've learned all about matrices, so now we can use what's called an adjacency matrix to represent a graph. So if you're going to do an adjacency matrix, you want your vertices A, B, C, D, E, F along the top of the matrix. You want A, B, C, D, E, F, so that you would have in this case, 6 vertices, 1, 2, 3, 4, 5, 6. So you're going to have a 6 by 6 matrix. And each time, in going across, I'm looking at A. Does A join to A? Well, no, that would be a loop. And this is a simple graph, no loops, no multi-edges. That's 0. Does A join to B? So I'd put a 1 there. There's one edge going from A to B. Does A go to C? Nope. Does A go to D? Yes. There's one edge from A to D. Does A go to E? Yes. Does A go to F? No. So that row tells me which it's an adjacency matrix. Ones represent adjacency. So A is adjacent to B, A is adjacent to D, A is adjacent to E. That would also tell me that A has a degree of 3 because it has 3 adjacencies. You can see up here it has a degree of 3. So B, we need to make sure it comes out to 4 when we're done. But does B go to A? Well, yes. Doesn't connect to itself. Yes to C. No, it does not connect to D. Yes, it connects to E. And yes, B goes to F. Again, you can see that would be a degree of 4 for B. C goes to A? Nope. C goes to B? Yes. C to C? No. C to D? No. C to E? No. C to F? Yes. We can see here, that's a 2 degree, and we can see here, 2 degrees. D would be yes to A, no to B, no to C, no to itself, yes to E, yes to F. E would be yes to B, no to C, yes to D, not to itself, yes to F. And that's a 4. Then finally F, which is also 4, doesn't go to A, yes to B, yes to C, yes to D, yes to E, not to itself. And that's an adjacency matrix. And then I can see on that adjacency matrix the diagonal here are all zeros because there are no loops. None of them connect to themselves. So if there were, and I'll show you that next, and you can also see their symmetry. 0, 1, 0, 1, 1, 0 would be A going down also. 0, 1, 0, 1, 1, 0. And you can look down the matrix and get the same information. B, adjacent to A, not to itself, adjacent to C, not to D, yes to E, yes to F. So it'll be a symmetric matrix when you do that. And always a square matrix. All right, so let's look at one more with that adjacency matrix. This time it's 5 points. A, B, C, D, E, 5 vertices. So we will need a 5 by 5. A, B, C, D, E. And looking at A does not connect to itself, not to B, yes to C, yes to D, not to E, 2, and it has a degree of 2. So yeah, B, not to A, not to itself, yes to C, not to D, yes to E, and again, it has 2. C connects to A, C connects to B, C does not connect to itself. We can see that C to D is a multi-edge. It connects twice, so I'm going to put 2 there for the 2 edges, and then not to E. And then if I add 1, 2, 3, 4, that's at a degree of 4. 1, 2, 3, 4. So D, same thing. Yes, it goes to A. Does not go to B. It does to C twice. Does not connect to itself. Yes to E. And again, that's 4. Look at E. E is no to A, yes to B, no to C, yes to D, but it has a loop. And it has one loop, so we're going to use a 1 here. So be careful, this adds up to 3. You can see the degree is 4, there are 4 edges, but because it has a loop, which is in that diagonal, it's going to count twice. So when you're doing this sum, if you have a loop, be really careful about that number. So that's 1, 2, that loop counts as 2, so it has a degree of 4. So if this is a non-simple graph, right, this is non-simple because it has a multi-edge, or it has a loop, or it has both, then be careful about that diagonal in your adjacency matrix. All right, so that's the beginning of graph theory. There's going to be plenty more vocabulary to go along, but this should get you started. And there's an assignment to go along with this first video. Thanks for watching and have a great day.